Hi, everyone, and welcome to Video AAPT. I'm Mike Hall, Director of Membership for the American Association of Physics Teachers. Video AAPT is a partnership between Physics Today and AAPT, and the sponsor of today's episode is Polyhedron Physics. Before we begin, let's go over just a few housekeeping items. At the bottom of your screen, there is a floating menu bar with shortcuts to the tools for engaging with this workshop. These are resizable and movable, so you're welcome to move them around to get the most out of your monitor space. At the far left of the bottom toolbar is the media player control for viewing the speaker. Also, you can expand the slide frame by clicking on the arrows in the top right corner. There are two different ways for you to interact in these workshops. There's the chat and there's the Q&A. If you haven't already done so, please feel free to introduce yourself in the chat, who you are, where you're located, what you teach. Although we will be monitoring and participating as much as we can in the chat, you can expect that the chat will largely be a conversation among the attendees. However, if you have a question or comment that you would like to get in front of the presenters, please submit that through the Ask Questions frame. I'll be monitoring the incoming questions and interjecting from time to time. We'll also have time at the end for questions. Please help us make this virtual workshop interactive by submitting questions throughout the event. If you are experiencing any technical difficulties, please feel free to enter any questions through the Ask Questions frame. A recording of the event will be available after the event concludes and can be accessed using the same audience link that was sent to you earlier. If you enjoyed the workshop, you could also share the link with colleagues so that they can view it on demand. Our first presenter of the evening is Eugenia Itkina from Rutgers University. At this time, it is my pleasure to turn it over to Eugenia.
Thank you, Mike. Hello, everybody. I will start sharing my screen. And while I'll be sharing my screen, let me just do it like this. You also received or will receive the link to the Google Slides, so you can watch again the presentation and play all the videos after we finish the webinar. And as Mike said, the title of my presentation will be Learn Physics by Practicing Science, or Introduction to ISLE. And ISLE is Investigative Science Learning Environment. And before I start talking about ISLE, I want you to see it. So these are high school students learning physics through ISLE. Looking at the photos, you can see some similarities. They're working in groups. They have small whiteboards. They're doing experiments. They're drawing on the whiteboards using multiple representations. And they're fully engaged in what they're doing. These are college classrooms in different universities: Florida International, Rutgers Central, Rutgers Newark. You can see the same picture, whiteboards, multiple representations. Students are engaged and sharing their ideas. And this is what ISLE Classroom looks like. But what are the students working on? In order to understand the process, I'm going to give you two examples in this short time. And we will start with an example of the ISLE process when no prerequisite knowledge is needed for the students. And we always start with the need to know. Those who are using Google Slides can play the video, but I'm going to play it here. A need to know is an experiment, usually exciting or surprising, or a question that students might encounter but never answered. And this question is posed at the beginning so that it creates the motivation for the rest. So do you see the candle and the screen with a little hole? So there's a candle in front of the screen with a little hole, and on the wall, surprisingly, you see a blob of light, and the students who are very attentive said, oh, it's the candle, upside down. How does the candle, upside down candle, appear on the screen? In order to answer this question, we are going to go through the whole unit. And at the end, you will be able to explain why we see the candle upside down. You are looking now at a completely dark slide. There's nothing on it. What is this slide? This is the experiment that we do with the students. We take them to an absolutely dark room with no sources of light. We don't ask them to predict what they will see. That is very important, no predictions. We ask them to sit there and observe. And if in your school, you do not have an opportunity to have an absolutely dark room, then you give this as a homework assignment before you start the unit. Go to a closet where there's no sources of light and sit there for 10, 15 minutes, 5 to 10 minutes, whatever you have the patience, and then report on your observations. The students come back and say, we didn't see anything. So what does that mean? It means that in order to see something, you need a source of light. But how does light travel? So the next question, and you are seeing the slide of team one of the students who worked on the following activities. We give them a laser pointer and we ask them to figure out how the light from the laser pointer reaches the wall. Some of them put the hands in front of the beam, and some of them use the water spray bottle that we provide to spray along the path, and they see that the path is a straight light. And then they answer the questions in the handout. And basically what they need to figure out that they don't see light itself, they only see the objects off which light bounces. And the beam of light from the laser travels in a straight line, and we call it a ray. So this is the first ray model, that the first model in optics that they encounter. And at this moment, we have the next step. What is it that we learned and what is missing? So we learned that light from the laser pointer travels in a straight line in the air. But what is missing is that what about other sources of light? How does light travel from them? And the next is another experiment that they do. We give them a frosted bulb or any LED bulb and ask them to turn it on. And what they observe, that the whole wall and the ceiling are now illuminated by this light. So they start discussing these possible models. How does this bulb emit light to reach everywhere? And they come up with this model, and your students will come up with this model. And this model is very common because that's what students see when they are kids and they're drawing the pictures of the sun. So what do we do next? We need to test it. And this is actually a slide made by the students showing the how their light bulb emits light. So they designed a testing experiment, and this particular group decided to cover the bulb with aluminum foil and make a tiny hole in it. This is the experiment that they designed. And then they need to make a prediction about what they will see when they run this experiment. Well, if this tiny spot sends a ray of light, they would see a tiny spot on the wall. They do the experiment, and to the surprise, and this is like, the result that we observed many, many times, students shocked. The whole wall is lit up. What does that mean? They need to go back and revise their model. And this is the new model that, in fact, each point emits multiple rays. Then they test it again using trying to use the shadows and see shadows and semi-shadows. I just won't go into the details, but basically they make a prediction that if they do the same experiment, the large area should be illuminated, and that's exactly what they saw. And what I'm trying to emphasize here is that they design one experiment, but they can use different models to make a prediction, and predictions are different. The predictions are not based on their intuition. They're based on a model. Think of how many opportunities your students have to make predictions of the outcome of the same experiment using different models. So the students usually reject the 1.1 ray model quickly, and then comes the step, return to the need to know. So how did we get the candle upside down, an enlarged candle? This is again the drawing of the students who worked on this problem. So now that they know that each point sends multiple rays, they showed how you can get the upside down image. And this is, again, the testing, and this can be another testing experiment, or it can be an experiment where they apply their knowledge to build a pinhole camera. And so now comes, again, the time for telling. What did we learn about the sources of light? That extended sources of light emit rays, multiple rays from each point. And you might be thinking, like, who cares, right? But in fact, we do care. If we do not understand this fundamental idea, then how do we draw images in mirrors and lenses, telescopes, microscopes, and all other optical instruments? So it is a very, very important concept. And by letting students go through this process, they really remember it. And so this process is a representation of the logical flow of the aisle approach, starting with observational experiments. Students identify patterns, come up with an explanation or a model or a quantitative relationship, design a testing experiment, and make predictions based on the model, not their intuition, of the outcome of this experiment. If there is a mismatch, they either propose a new model or say, we need more data, we need to conduct more observational experiments, we're not even ready to create a model. And if there is a match, then there's more testing experiments. And finally, we proceed to applications. This is not a just circular thing. It is going back and forth between different steps. But this approach works for any concept in a general physics course. But there's more to it. You saw how important the idea of array, of a graphical representation was for them developing the model. And so we have a library of multiple representations for all topics of the course. But there's more to it. Not only students work in small groups and share their ideas with the rest at the end, which builds a community, but they have opportunities to improve their work without being punished for the second or third try. Not only in the process that you observed when students first came up with a model that didn't work and then developed a model that did work, they had an opportunity to revise their reasoning, and this is a normal process. But we also structure our courses that students have opportunities to improve their homework, lab reports, quizzes, and tests. And their grades are not lower because it is a second or a third try. They reflect what students know or are able to do at the moment. Why? Because the aisle approach is an example of an intentional approach to curriculum design and learning. What does it mean, intentionality? Intentionality is a purposeful mental state of a teacher that guides all of our decisions about what we do in the classroom, about activities, assessment, course goals, classroom setup, and even how we interact with the students in the classroom on a minute by minute basis. And so if your curriculum is intentional, that you need to be very clear to yourself what these intentionalities are. So we have two. Students learn physics by practicing it. This is one, because we understand that the medium is the message. If we want the students to learn the process of physics, they have to be engaged in it as they're learning it. And the second is the students' well-being enhanced by this learning. And this is based on the theories of human motivation. People will only learn if they enjoy it, and they see value in their personal lives, experience learning as an opportunity for mental and spiritual growth, not think that they cannot do physics, they do not belong, and it's just not something for them. If you're interested more in the whole philosophy and approach, here's the book. It's probably in your library. It's called Investigative Science Learning Environment: When Learning Physics Mirrors Doing Physics. We also have a textbook for algebra-based physics that comes with the active learning guide with activities that you just saw there in the active learning guide, the active learning guide for teaching online, lots of videos. All this is free, including the instructor guide and the textbook that comes with all of this, but you can use the active learning guide and all the videos, all experiments without the textbook. And the website where to learn about all this is aislephysics.net. There's also a Facebook group with over 2,500 members now from all over the world, where there are everyday discussions, professional development, online free workshops every month, and more workshops in the summer. So if you're interested, join the Facebook Exploring and Applying Physics. So now I'm going to show you another example of a sequence for another concept. But this is a concept before which students need to do some learning. So the example is for circular motion, and you need to imagine that your students studied kinematics and dynamics of linear motion, three Newton's laws and their applications. So what should students know before starting this unit? How to draw motion diagrams, most importantly, what the velocity change arrow means on the motion diagram, how to add vectors, how to determine how many forces are exerted on an object of interest, the system, how to draw a force diagram, how to label forces on the force diagram, and Newton's second law as acceleration is the sum of the forces divided by mass. Okay, so this is just a summary of how we teach the students to construct the force diagram. Identify a system, the interactions with it, with objects outside the system, and then represent these interactions with arrows. And the intensity of interaction should be reflected in the length of the arrow. And each arrow is labeled with two subscripts: force that sand exerts on the rock and the force that earth exerts on the rock. And you will see how important this labeling is in the example that I'm going to show. And as always, we start with the need to know. The whole video is amazing. And if you haven't seen it, it's right here, the link in the Google Slides. It's Damian Walters trying to run loop the loop. Several trials he fails, and then eventually he is able to run literally upside down. So the question is, why did he need so many tries? And why was a specific speed needed for him not to fall off on the side or on the top of loop the loop, which you can see in previous trials. And for this, we again start with observational experiments. And remember, for observational experiments, we do not ask for predictions. It is not predict, observe, explain sequence. It is observe, find patterns, explain, and test your explanation sequence. Very different, right? So the students do the following experiments. It's best if they do them in a lab, because the first experiment is a lot of fun for them, and it takes them some time to do it. The goal is to get a bowling ball to move in a circle. And this guy is doing it, very easily, but it's not easy at all. Like, I cannot do it no matter how much I try. But students figure out in 15, 20 minutes, they need to kick the ball perpendicular to the circle, not along, which they try to do at the beginning. Then they take their backpacks and they swing them in a circle. And again, they need to analyze the forces exerted on the backpack and the forces exerted on the bowling ball. The third experiment, if you rollerblade, you can repeat it. This is me on rollerblades. But if not, you can show the video. It's online free. So here's me moving in a circle. Watch my skates. I'm not doing anything with my feet, and yet I'm able to move in a circle, and the rope pulls perpendicular. So the students do these experiments or watch them, and then we ask them to draw the force diagrams to represent, to analyze the situations. These are real force diagrams drawn by a team of students when they were learning online. So I have the slides for that. And you can see how they label the forces with two subscripts. And at the end, they identified a pattern. The direction of the sum of the forces exerted on the object, the sum of the forces is towards the center. We didn't tell them, they figure it out by themselves. This is my perfect analysis, looks a little better, but it's the same. So the students were able to produce the same analysis as I did. So now the question is how to summarize your pattern. There must be the sum of the forces pointed toward the center when an object moves at constant speed in a circle in all three experiments. So here's the pattern. But it's not enough to find the pattern, you need to test it. So now we ask them to think about the following experiment. Imagine you have a ring and you want to roll a ball inside it. Would it be possible to roll a ball without touching it inside the ring? And that what will happen when loop is open. Again, this is the analysis of the students. So they draw a force diagram before the removal of the part of the ring, and they said, well, the ring pushes perpendicular to itself, so it's perfect for circular motion. And after the removal, you see the force diagram is just nothing. So the object has to go on a straight path, and this is the aerial view, right? So now we can do the experiment, and we just buy these cheap pie pans, and then they all do the experiment on their tables if they're in a lab or in the small classroom. And they're so happy that the ball actually moves in a straight line. You cannot imagine the excitement. So now that they tested this explanation, the question is why? Like, why is that? Why do we need the sum of the forces pointing towards the center? Is there an acceleration? And somebody will say, no, there's no acceleration because it's constant speed. But somebody said, wait a minute, the object changes direction. And once they say it, then we do the following experiment to see whether this is true. This is what students do when I'm in the classroom. I do it on rollerblades. Here's the video of me just walking in a circle with a meter stick. The meter stick shows the direction of motion. And you can see that at every point, when I'm moving in a circle, the meter stick is tangent. This is a very visual experiment, and students can clearly see what happens. And if we draw several circles, then they start running along, and they taking videos, and they take the slow motion videos to actually see that the object changes direction. And now comes time for telling. If there is a change of direction in the velocity vector, then we can find acceleration using the method that we already learned in linear kinematics. So to find the final velocity vector, we see what we need to add to the initial. And here we say that at a point, the direction of acceleration at a point needs to be determined using before and after velocity. And the process is shown here. And because acceleration is change in velocity divided by time, and time as a scalar, the direction of acceleration is the same as the direction of velocity change. So now they have a tool to find the velocity change. We put them into teams again, and each team gets 1 point on a circle to find the acceleration using this method. They practice it right away. And this is what team 3 did in their classroom. And you can see that they found that the delta V arrow points toward the center at point C. And another team found it at B, A, and D. And so now the class comes up with an idea that because the pattern in the acceleration vectors is all towards the center, it is understandable and makes sense that the sum of the forces is towards the center. And here comes time for telling, when the teacher summarizes what the students did. So now we can test the ideas in a new experiment, but I'm going to skip it. You have it because the time is short. And you're thinking, like, what about mathematics? Like, when did they figure out that velocity, that acceleration is v squared over r? We have, again, a sequence of very similar activities. It's just not no time in this workshop. So what do students say about this method? These are quotes from the interviews of many students who took an IELTS-based course. So when they talk about a course in a free interviews, they talk about what you learned, what you think was good, how does the course compare to other courses you took. The most common themes that emerged is that every student mentioned that what they learned in the course is useful for other courses, future profession, or everyday life. So even if I'm in a class where the professor, like a robot, just talking, reading PowerPoints, I can go home and turn it into something that's going to be interesting to me because you guys, the teachers, made us think about how we learned and what the best way to learn is. They talk about the role of experiments. By the way that we learn these things, it's not as hard as what the regular physics students, they're like, oh my God, this equation is so difficult to derive. But our class, we're like, well, it's easy because if you grasp this and you think about the situation when you get this, and it's cool because we got to do all those experiments and we understand already how it works. they appreciate the opportunity to figure things out. It was a learning process because I was so used to be fed information and remembering it and repeating it that here at the beginning, I didn't like it because I was not shared information. I said, what the heck is this? How am I supposed to learn anything? The professor didn't tell me anything. And I was so used, you're so accustomed to being fed all this information and memorizing that you have no idea what's going on. Here I have to figure out what's going on, and then a true understanding could arise. And many of them, especially females, spoke about affect. I definitely do enjoy physics. In terms of interaction and stuff like that, I like physics a lot, a lot. At first, I come to class and I'm like, oh, what crazy thing are we going to do today? Let's see what happens. And then when we're actually doing it, I'm just so hyped and I'm so excited. And magnets, I love magnets. My magnets, oh, those are my babies. I love my magnets. But with magnets and with mirrors and with lenses, it was exciting. It was cool. And it was like, I knew I was going to leave with something that was going to blow my mind. So, where to find the resources to implement the IEL approach? Again, ielphysics.net. I also have a link in your slides to the participant folder with a lot of materials that you can use right away. There's another site where you can get IEL-based labs and all other activities and self-assessment rubrics. There is another site where you can get more videos with questions. There is an offshoot of IEL for high school and middle school called Physics Union Mathematics, or PUM. These are all free materials. And I wanted to show that it's not just me. There's a lot of people who have been contributing for over 20 years to the development of these materials. There's also a podcast about IEL. And recently I published a Physics Today article about IEL. So I put all the links in the Google Slides that you can access them easily. Thank you. If you have questions that I don't have time to answer today, please send me an email. Now I have to figure out how to stop sharing my screen. Okay. Did I stop sharing my screen?
Yes. Thank you so much, Eugenia. There are a couple of questions. Let's see. Joanne was asking, and this is from early on in your presentation, are different rough and smooth surfaces used for the optical experiment?
Say it again.
Are different rough and smooth surfaces used for the optical?
Eventually, yes. When they study reflection, of course, we use mirrors and we use walls and everything. Of course, I just showed you a little part for one concept, for one idea that each point emits multiple rays.
Great. Okay. And then there's a question from Bill. He wants to know how this very interesting approach squares with the need to cover a suite of topics within the time constraints of a typical high school schedule, especially when students are faced with a year-end exam such as AP Physics. Right. He's saying, he finds this approach very attractive and ideal, but how do you make it realistic?
Right. Well, a lot of teachers use AP, use our approach and our materials for AP. And there are several things that I have to say here. First, at first, we move slowly because students are getting used to actually thinking. And then once they grasp the method, they move very fast. So it's not that we cover less material, we uncover more material. Another thing that we do, and I did not talk about it here, is that using our textbook, students are taught elaborative interrogation method, how to work with the textbook. So you don't need to teach everything in class. After the first 6 months of learning how to read and work with the science text, they are able to study certain things on their own, and you only ask them questions. So there are multiple ways of shortening stuff, and I run workshops on how to move faster. So if you're interested, join the Facebook group, attend the workshops, and you will see how it goes. But nobody suffers from the lack of coverage, but everybody benefits from the increased learning.
Okay, let's see. I think we have time for maybe one more. there's a question, what is the cost for doing these labs? Is it relatively low budget?
The labs, well, it's not a lab curriculum. It is a holistic learning environment. And it's better, well, it works perfectly when the labs are integrated, because in the lab, students do observational experiments, then they go reason in a large room meeting if it's a large course, or if it's a studio environment, it just moves smoothly. In a high school, you don't need to even think about it. You just do experiments and reasoning, and it all flows. All the activities are free. And if you need to know how to access them, join the Facebook group. And the Scientific Abilities website is free. You can get all the labs, but the labs by themselves don't do it. You need the whole thing implemented so the students know how to develop ideas and test ideas. Although, if you are teaching a large enrollment course and you only can remodel the labs, we have this experience too, when you can just take the labs, implement them in the lab, and have traditional lectures. It's less effective, of course, but it's better than cookbook labs. Everything is free. Again,
Okay.
Send me an email, join the Facebook group. All these questions I answered every day.
Thank you, Eugenia. And there are a few more questions kind of piling in, and I think if I can kind of float them to you over the next few minutes, but I think we're going to move on to our next presenter, which is Jean Finstein with Polyhedron Physics. And so I'm going to pass the mic over to Jean. Jean?
Okay, hi, thanks, Mike. I appreciate that. Interesting, Eugenia. We really think your IL method can serve to help inspire some students, get them curious and engaged, and that can be half the battle for sure. I am joined this evening by Russ Sellers. We are part of the development team for Polyhedron Learning Media. We're an educational software development company. And also joining us on this webinar is Al Bachner, who teaches at Nassau Community College in Long Island, New York. You should be seeing our homepage, which is polyhedronlearning.com. And as we scroll down that, you'll see several of our products. And what we'll be talking about this evening is our Polyhedron Physics options. This is the Polyhedron Physics homepage. We will note that the Polyhedron Physics labs and simulations were developed with funding support from the U.S. Department of Education. Anyone attending this seminar can access a free trial, and Mike will be putting the link to that trial into the chat, but you can go to this page, which is polyhedronphysics.com/register, and click on free trial, and you will be able to access that. So it's a 30-day free trial available to anyone on this webinar. We also, on the pages, various pages, will have a send us a message button. So if you have questions after the webinar that we don't have time to answer, we will certainly get to them as they come in. Now, in order to briefly explain what polyhedron physics looks like, we will show a very brief video.
Polyhedron Physics offers an effective way to provide realistic lab experiences at the secondary and post-secondary levels. Online access, anywhere, anytime, makes these labs ideal for distance learning or homeschool situations. Two product options are available, Polyhedron Physics and Polyhedron Physics Plus. Both include interactive 3D simulations that allow students to manipulate virtual lab equipment, conduct experiments, and collect data in a realistic way. Polyhedron Physics simulations include only the instructions for manipulating the virtual equipment. This option is best for instructors who prefer to use their own experimental procedures and evaluations. Polyhedron Physics Plus labs are complete, with all necessary supporting materials included: experimental procedures, background theory, data analysis and reporting tools, pre- and post-lab quizzes, and a teacher guide with notes, quiz answers, and sample lab reports. Each Polyhedron Physics Plus lab also includes a video introduction showing an overview of the lab being done by a student with real equipment. Whether you need a complete, ready-to-use lab package, or you just need the virtual equipment for use in your existing labs, one of these product options will be right for you. With more than 60 simulations in the areas of kinematics and dynamics, thermodynamics, electricity, and light and sound, Polyhedron Physics can easily cover an entire year of physics labs. Interactive 3D simulations allow students to manipulate equipment and collect data just as they would with real equipment in a hands-on lab. Variability and error based on real-world data make these simulations realistic in every respect. Polyhedron Physics can be used in a variety of learning environments. Students can use the labs as a supplement to traditional hands-on labs, or as a replacement when hands-on labs aren't an option. They are ideal for use in distance learning situations as well as by homeschool students. And by eliminating the need for expensive lab equipment and time-consuming setup, Polyhedron Physics offers an economical alternative where resources are limited. Most importantly, Polyhedron Physics labs are effective, as shown in independent evaluations at both the college and high school levels. Polyhedron Plus apps are also available on iPad, where they provide the same features as the online versions. iPad apps can be purchased individually or in bundles. Educational pricing is available. Be sure to visit the Polyhedron Physics website for more information and a free trial. Polyhedron Physics, the next generation of physics labs.
Unmuted. Okay, hopefully everyone can hear me. This is Russ Sellers. I'm a member of the Polyhedron Physics Development Team. I'm going to go quickly through some of the simulations and laboratories that are available in Polyhedron Physics. The simulations first are grouped in kinematics and dynamics areas, and you can see a lot of the different simulations that are available on your screen. I'll just scroll quickly down through those. We'll look at them in more detail in a few minutes. There are simulations in the areas of thermodynamics. There are simulations in electricity, simulations in the area of light and sound, and physical optics and nuclear physics. In the Polyhedron Physics Plus laboratories include a lot of other resource materials in kinematics and dynamics, in thermodynamics, in electricity, and light and sound. And what I'd like to do is look at a couple of these quickly. I'm going to bring up a addition of force vectors Simulasics Plus laboratory. It's a 3D model of a force table you probably recognize. And you can rotate it around, look at it in different angles. Along with the Polyhedron Physics Plus lab, additional resources, including a laboratory manual. Is a set of objectives for the student to do a laboratory. There's a theory section that's a review of the material they would study before the lab. There's a pre-lab quiz that the students can take to assess their readiness, and there's a self-evaluation at the end. There's a list of the equipment the student will use for the simulated lab or with the real equipment lab. There's a set of videos that the student can watch that shows a student doing a lab with real equipment. There's a set of hands-on procedures. If you're going to use real equipment, you can follow these procedures to do a addition of force vectors lab. And then after the student finishes the lab, there's a set of post-lab questions that ask them questions about their results and extend the concepts that are taught during the lab. Okay, back to the simulation. Students seem to never have much trouble figuring out how to actually operate the simulation. But if you would like to see how to operate some of the controls, if you can't figure out how to do something, there's a set of instructions that are available that you can click on. It's not popping up here. Yeah. So we'll skip through that for now, and we'll move on to the actual demonstration of the simulation. The instructions are going to tell the student to record the values in the table of the masses and angles for the force vectors that are going to apply to a ring at the center of the table. And we'll start out with putting 150 grams on pulley A. We can put 200 grams on pulley B. And you can go to a top view of the table and set the angles that they're told to set in the procedure. I'll put pulley A at a direction of 0 degrees. I'll put pulley B at a direction of 90 degrees. I can go in using view controls and set those more precisely to bring pulley A precisely at 90 degrees. Sorry, at 0 degrees. Pulley B precisely at 90 degrees. And then I can go back to a top view of the table. I'll rotate pulley E, the equilibrium vector pulley, around to a direction that brings the ring like it's in a direction close to center. And then I'll start adding some masses to that pulley. And when I add the proper amount of mass to that pulley, I'll get close to a set of balanced forces. I can move the ring around, and you can see that there's some friction in the pulleys. It doesn't quite center up, but you can get it to where it generally centers as you move it around. And then the values you've put on the different pulleys and the different directions of the forces, you can enter those values into the table. You can calculate the component forces and come up with a value for the resultant vector. And then from the equilibrium vector, you can determine an experimental value for that resultant vector. And you can find the percentage of error in the difference in angle of the direction of the vector. There's also the ability to do experiments with 4 pulleys on the table. And there's a simulation available where you can put 2 or 5 pulleys on the table. All right, now I'd like to demonstrate. Okay, that didn't work.
Click on the screen, main screen.
Yeah, I'm trying to find, there it is. All right, let's take a look at a gas laws, polyhedron physics plus laboratory. This is a 3D model of a syringe with a cylinder supported on a beaker. There's a plunger on the table. There's a set of kilogram masses on the table. There's a hot plate, a bucket of ice, and there's a barometer on the table. And to start the experiment, the student would take some preliminary measurements, measure the diameter of the cylinder syringe, and enter that in the table. The first part is a demonstration of Boyle's law. You can also look at the barometric pressure. There's a barometer on the table. You can take a look at the barometric pressure and write it down. And there's also a blow-up of the beaker that's near the thermometer. We can assemble the apparatus, which puts the plunger in the cylinder, put some masses on top, and you can look at the volume in the syringe for different forces, different masses on top, and record those in the table. And when you complete the experiment with different pressures and volumes, you can produce a report that looks something like this. Is the Boyle's Law lab report that shows you the inverse of volume versus pressure graph that the students can produce using the lab. All right, another lab that I can demonstrate is with the same simulation here. we can do a demonstration of Charles' law. And what we can do is we can add water to the beaker. You can add ice to the beaker. There's a stir, and you can start the temperature decreasing, as you can see on the blow up of the thermometer on the left. There's an advanced time feature that speeds things up considerably, so you can advance to where the temperature is close to zero, and you can go to the syringe, measure the volume.
Excuse me, Russ.
Sure, Al.
Excuse me, Russ. Al Bachner here. Just wanted to mention to the viewers that the noise that they're hearing is actually the sound from the simulation that's giving student feedback about the ice being stirred. And we should apologize with the platform that we have here with the Elite Studio. I don't know that that the simulations are being shown smoothly. But as a user of these simulations, I'll tell you that the simulations perform on any of the platforms, whether it's Apple or iPads or whatever it is. They perform very, very smoothly, and the sound and the visuals are all enhance the experience. I'll let you go, Russ.
Yes, and I will say this, Gene, that when we tested this with students and the steam was coming out of the beaker, that one student actually put his hand on the computer screen to see if it felt hot.
With the data the student can get from that Charles Law lab, they should be able to demonstrate Charles Law and also extrapolate to a value of absolute zero. We have lots of different labs we can show you, but what I'd like to do is go through some slides of some of those different labs. So this is an example, a screen capture of the image formation using lenses simulation. It demonstrates some of the same principles that Eugenia talked about with her ray optics demonstration. The Newton's second law of motion lab is one example of a polyhedron physics plus lab that uses a cart and pulley system. There are several labs that use that. There's a centripetal force, a couple different centripetal force simulations in labs. There's a lab on Joule heating, a lab on series and parallel circuits, a lab that allows you to use a resonance tube to do the speed of sound.
Now, what Ross just demonstrated to you were just 2 of the 24, what we call polyhedron physics plus labs. These are the ones that have all the resources available for students and also for instructors, including sample lab reports, post-lab quizzes, sample answers to the open-ended questions, for example. Also, each of these 24 Polyhedron Physics Plus labs is available on iPad. We also have, in addition to that, 45 simulations. These simulations are for instructors who want to use virtual equipment, but want to use their own procedures or lesson plans. And so Russ will just demonstrate, or not demonstrate, but just go through some screen captures to show you what some of those are.
Yeah, I hurried through a couple of the rotational equilibrium simulations. There's a simulation that does collisions for conservation of momentum, conservation of energy using an Airtable. Some of the simulations are of equipment that's pretty expensive and difficult to acquire, and so some of those would be really handy for expensive equipment. Here's a simulation involving the principles of how thermometers work. There's a Kirchhoff circuit laws apparatus simulation, a Wheatstone bridge simulation, an electric field mapping apparatus simulation, a long straight wire induction apparatus, a ray box and triangular prism, standing waves on a string, a resonance chamber, and a wavelength of light apparatus. And here's another expensive one. We have a Geiger counter and samples where we can do absorption of radiation with lead absorbers and polyethylene absorbers. We also have one that uses a Geiger counter that looks at the half-life of a barium sample.
Okay, so this is, again, the Polyhedron Physics homepage, and you see the URL down at the bottom. If you go to that page, then you can sign up for your free trial. And we'd like to show one other lab, one other simulation actually, and it is on projectile launcher. And this is where Al will kind of describe some of his experiences using our simulations.
Thanks, Gene. I'm sure that many physics classes use a projectile lab, and generally what I've seen is that they typically use a projectile lab that considers range. At NASA Community College, many years ago, we introduced an idea to not only capture range, but capture height of the projectile at different ranges. And when we developed the equipment, we found that it took students a lot of time to set it up, because each time the target was rather small, the impact pad, and that was the target, and students had to take 3 or 4 test shots to zero in, get the target at the proper location. What Polyhedron did was they took our equipment and they went ahead and designed this virtual lab. And they came up with a brilliant idea. They made the target very long. That eliminated the need for the students to zero in the location of the target relative to the path of the ball. Also, some of the advantages here, I see that Bill and fellow Tommy were very interested in conserving time or using it effectively. And if you've run a lab like this, you know that students spend a lot of time crawling under desks and under tables to retrieve the projectile. So with the simulation, there's no need for that. Now, also, you could use the simulations if you, many instructors at the college like to use the simulations simply to demonstrate to the students how the lab will work, and then have them do it with the regular equipment. Other instructors like the idea of having a simulation where each student can sit down at a computer and control their own equipment and be assigned an individual set of circumstances. Like for the projectile lab, maybe Russ, you could show how we can adjust the angle of the firing mechanism. And each student can have their own angle, and also in the simulation that can be adjusted to different angles. And in the simulation, we have Polyhedron has 3 settings for the launch of the, it has a spring launch, and it has 3 different settings. So we can give the students their individual settings, so that how many times have you had lab groups and they go ahead and you got 4 people in a lab, and you got 1 or 2 people working on a lab, and the rest of the lab group is checking their social media. This keeps each involved, and you could, of course, let them work in groups. When we were working remote during COVID, I assigned this lab, and what I did was we were using Zoom, and I placed each group in its own meeting room and let them work as a group, and went around and checked on them. Some of the other, can you go back and show the target path sheet? This will very quickly demonstrate that. Oh, you only have 1 shot up there. Okay. If we had several shots, we'd see a variety of or locations that demonstrate the experimental variability that's programmed into each of the labs. So the labs aren't simply running equations. On some of the older labs that we were using for this, when you shot a projectile, it would land in exactly the same height at exactly the same range. each time. Now, Eugenia was talking about having students discover things. One of the things we like about this lab is by having the students do a graph of the range versus flight time and a graph of the height versus flight time, they can very quickly see that there is a difference. The range versus flight time is linear, while the height versus flight time is a polynomial, and they can through graphical analysis see that the acceleration in the horizontal direction is 0. Now, also in with this lab, with each of the labs, as you noticed in the force table lab, there are places on the screen that record some of the data for the students and makes data recording easy. Russ mentioned the cost and maintenance of the equipment. How many times have you have 5 or 6 lab groups going, and one of the lab groups right in the middle of the lab, the equipment just fails. Now what do? Well, typically you divide up the group, and they have to void all their data and join different lab groups. Here that you don't have that problem. The labs always work. In fact, another advantage of this is, yes.
Yes, Al, thank you. I think we only have a few minutes left, and
Okay.
so perhaps we could take some questions at this time.
Sure, there are a few questions in here. There's a number of questions that pertain to the pricing of your products and that sort of thing. I think perhaps those would be better to be answered by separate email. But I wanted to get to a couple here. One question from Andrea is, can polyhedron physics be integrated into an LMS?
Learning management system? I don't see why not.
A learning management system, it should be able to. And as far as the pricing is concerned, we briefly showed a page there, but we can be creative with different pricing options. This is all web-based, and so making it fit into an LMS shouldn't be a problem.
Well, Gene, what I do in my class is we give the students the website. Each student registers, is given a registration number and has their own account, and they can access the lab from any computer anywhere in the world. And if they miss lab in class, they don't have to arrange for a special setup. They can do it at home or on vacation.
Right, and quite often students may be involved with sports. They may be ill, they may miss a lab, and it would be difficult to set up the lab equipment and schedule a time for them to come. Also, when I took physics, I remembered that my lab partner was very good and basically ran the experiment, and I was sitting there watching, and I could see what happened, but I wasn't really able to get my hands dirty in doing it. And with this, I can go home and I can play around with it myself. I can try different input values. I can see what happens on my own without my smart lab partner doing everything. And I can do it as many times as I want.
Okay. And Gene, we do have time for one or two more, I think. But if you could, I think if you stop sharing your screen, then we can see you again. So you may want to do that.
Okay.
There's a question: does polyhedron allow for LTI integration?
I'm sorry, I don't know what that is.
Okay, we'll see if Eric wants to elaborate on that. In the meantime, let's see. Hold on, I just lost my place here. Are the labs auto-graded?
No, they are not auto-graded with the exception of the pre-lab quiz. And the pre-lab quiz is something that the students would take on their own, and the answers are provided along with explanations of the answers. Otherwise, they are not, they're not self-graded.
Interesting. Okay. And let's do one more. If the college physics lab is 1 credit, what is the faculty teaching equivalent for teaching the online physics lab?
Well, that would be up to the institution.
Sure.
Yeah, we tried to model these so that we had a wide variety of options, and we think there's just about everything that you would need for an introductory physics course. If that is what the question related to.
I think so. Yes. And let's just do one more. This is from the chat. Someone is asking if there is an app for Android available.
No, not yet.
What?
We're entirely web-based or iPad.
Okay.
And before we quit, I would like to thank everyone who participated in this. Eugenia, you were the perfect startup for this webinar. And of course, we'd like to thank AAPT and Physics Today for making this possible. And I'll remind everyone that this is recorded, and so you can go back and watch again if we went too fast or if you wanted to have something clarified.
Thank you so much. We are at the top of the hour, and we want to be respectful of people's time. Jean, there are a number of additional questions that I think just for anyone who asked the question that we weren't able to get to, we can get those questions to Jean and the polyhedron team, and they can follow up with you afterwards or in the next day or so. But at this time, we're going to wrap things up. I want to let everyone know our next episode is going to be on April 18th at 7 p.m. Eastern, and that will be sponsored by Vernier. We'll have more information on this in the very near future, but for now, if you could please save that date, April 18th, that will be the next video AAPT. Thank you again to our presenters, Eugenia and Jean and the Polyhedron crew. Thank you so much to Polyhedron for sponsoring this episode. Thank you to Physics Today for working with us on this project. And thank you all for attending. Have a fantastic evening, everybody.
Thank you.